This is for the Unit 3 conceptual questions, page 7 and 8. So number 22 is similar to where page 6 left off. So we are taking the forces, right? We're taking the sum of forces in the x. So for our F3x, instead of putting that in our statement, because it's adjacent to angle 3, right, it would be F3 cosine theta 3, and we're putting that in instead of F3x, which you can see in the statement, and then F4 is acting to or pulling to the left, so it's negative 0.4. So if we're looking at the forces in the y direction, see if I can get rid of those, we have our F3y, and because it's opposite, right, it would be F3 sine theta 3, and it's pulling up, so it's going to be a positive force. Our F1 is pulling up, so it's going to be a positive force, and our F2 is pulling down, so it's going to be a negative force. So we have two positive forces and one negative force. So over here on the next one, it's the same idea, except for notice now that we have a tilted x and y axis, so this must be an object on a hill, essentially, or something similar to that. So our F2, we're going to have to split into F2y and F2x, and whatever this angle is going to match up to here. And so our F2y is going to be F2, and because it's adjacent, cosine theta, and that's it, just cosine theta, right? And our Fx would be F2 sine theta, because it's this force would act the same as if it was down here, so it's opposite of that angle. So you can see that our F2 sine theta is in the x direction, our F2 cosine theta is in the y direction. Because this is pulling down, I made it negative. Because this is pulling left, I made it negative. And then our F1, of course, is right along the y-axis. And so F1 is here. And that gives us all of the y forces. And now we have the only thing left would be, let's see if I can erase here real quick. The only thing left would be our F3x, right, and our F3y. And if this is from a horizontal and our F3 is going horizontal, then the angle would match up. And so our F3x would be adjacent, so it would be F3 cosine theta, right, which is, where is it at? There it is. And it's pulling to the right, so it's positive. And our F3y, because it's the opposite from that angle, would be F3 sine theta, right? And that is here, and it's a negative value because it is pulling down, and that's why it's negative. That one was a little bit harder than the rest of them. Okay, 23 and 24 are a little bit different than what we've been doing, but they want us to draw a vector on the arrow on the grid starting at the origin that shows the net force. Well, we were doing that before. If there is a force in the x direction of 3, right, this would be a positive 3, and then the F2 component in the x direction, right, the F2x would be negative 2, then we know that the net force in the x is positive 1. And then in the y direction, right, the F2y is positive 2. So we know the sum of the forces in the y have to be positive 2. and now we're going to put those things together. So we get let's see if I can erase all these marks. So we need a line that goes to the right 1 and up 2, right? So to the right 1, up 2. So this green force represents our net force. Now, if F equals ma, then A equals F over m. And if we want the acceleration just in the x direction, we would use the net force just in the x direction. So we said that the net force in the x direction is 1, and it's over a mass of 2, so 1 divided by 2 essentially is doing our F, right, over m to get the acceleration in the x. And the same thing in the y. We said that the net force in the y is 2. It's over a mass of 2, so I got these right here as the net force in the y and the mass of the object to get the acceleration. So that's what I did. The same thing here for number 24. So looking at number 24, it's very similar. We are going to take in the x direction, let's say we're just looking at, right, we know that F2 is pulling to the left at -1. We know that F3 is pulling to the left, and that's another -1. And we know that F1 is pulling to the right at 3, so that's +3, giving us a total of +1 in the x direction. And so again, this statement here is the net forces in the x over the mass of the object, right? So 1 over 2. In the y direction, we are going to do the same thing, right? So now the sum of the forces in the y, we know that F2 is +3, right? F3 would be -2, and F1 doesn't do anything, so we know that it's +1. So again, it's right. The 1 is the is the net force in the y, +1. 2 is the mass, again because we're using this idea of A equals F over m. Moving on to our page 8. Right now it's giving us accelerations and it wants us to put in the net force, right? That would, where is it here? Not the net force, but 2 forces are shown, a third is missing. Draw and label that force so that you get these accelerations. So we need in the x direction to have an acceleration of 2, and we know that acceleration is the net force in the x direction over the mass, and it tells us here that the mass is 1. So that means if we want a net force, or if we want an acceleration of 2, we have to have a net force of 2. So if you're looking at this diagram, right, in the x direction, this would be, right, in the x direction we have a +2, and over here we have a -2, so we need a net force of 2, which means we need to add our vector, whatever vector we're going to add needs to have in the x direction a force of 2. So looking in the y direction, right, in the y direction we have F2 as going up 2. We have F1 of going up 1, and that's it. So if we want to have an acceleration of 0, then we need to subtract 3, right, so we can get a net force of 0, so we can get an acceleration of 0. So that means I need in the x direction to go over 2, and in the y direction I need to go down 3. So you can see my green or my blue vector here, right? I said I went over 2 and down 3. So I knew that this was my force 3 that would cause those accelerations. And 26 is basically the same thing. Right in the x direction, we need the forces to be 0 if it's not going to accelerate. So our F1 is plus 1. Our F2 is plus 1. So we need to have something be negative 2 so that it equals 0. So we know that is our x force, right? Because we need this to be a net force of 0 over the mass. For our acceleration of negative 3 in the y direction, we need a net force of negative 3 because it's a mass of 1, right? Because we're using A equals F over m. So we need our force in the y to be 3. So looking at our diagrams, right, in the y direction we have a force of plus 2. And in this one we have a force of negative 2. So we need, right, we need it to be negative 3 total. So we need now a y force of negative 3 so that it equals a total net force of negative 3. So we can get an acceleration of negative 3. So that means, right, that I need a net force that goes to the left 2 and goes down 3. And so that gives us our F3. Number 27 says the object moves with a constant velocity. That means the net force in the y and the net force in the x have to be 0. If F1 has a force of plus 1 and F2 has a force of plus 2, then we know I need a force that is going to be, negative 3 in the y direction so that those net forces are 0. In the x direction, we already have the x component of F2 as negative 2 and the x component of F1 as positive 2. So negative 2 and positive 2, that's already 0. So all we need is a force that's moving in the y direction at negative 3. 28. Suppose that you have a jet-powered flying platform that can move straight up and down. For each of the following cases, your apparent weight is equal to, greater than, or less than your true weight. Well, your apparent weight is basically saying, right, we want to know, is the normal force equal to, greater than, or less than? The weight of this guy does not change. Right? He has the same mass, he's on Earth, so he has the same weight. So the only thing that can change is how the ground is pushing up on him, and that gives you this apparent weight, or your feels like weight, what we were talking about in class. So if you are ascending and speeding up, right, so you're ascending, you're moving up, and you are speeding up. So if you have weight and you are speeding up, going up, you need your normal force to be greater than your weight, right? So because you're accelerating up, the net force needs to be up, so the normal force, which is your apparent weight, must be more than your weight. Part B, if you are descending and speeding up, so now you have your weight again, but because you're going down and you're speeding up, this weight has to be more than the normal force, right? So the normal force is going to be less than your weight so that the net force is down and you move down. Hope this helped. And hope this helped, and one more video for pages 9 and 10.